Okay, let's start with question number 8 from the IMONS level 2 reading material 2021. Okay, so simple digits, hopefully. Okay, let's try number 8 first, please. So find all integer solutions to 2 to the power of x minus 1 equals to 3 to the power of 1. Okay, we'll find all integer solutions to that. So the first step would be to, let's say we kind of rewrite it like this. Okay, let's leave it as it is first. And then we do a modulo 4. That means I want to split the cases where, let's say, x is less than 0. And then the 3 cases that I want to talk about. What if x is an integer less than 0? Okay, so the first case, let's do part by part, and perhaps then it will make sense. So if x is less than 0, what happens is, let x equals to, let's say, a negative m, where m is a positive integer, m is bigger than 0. And then this can be rewritten as 2 to the power of negative m minus 1, which is obviously less than 1, because we can see the next line by writing it 2 to the power of m like that. So it equals to this 3 to the power of y. And it actually forces the y to be also less than 0. Okay, because if y is not a fraction, or in other words, not less than 0, and then we have a contradiction. Because the left hand side is less than 1 and the right hand side will be at least 1. So that is why we let what we say y equals to negative n, where n is a positive integer likewise. So I'm just making it a bit simpler writing style now. So we have 1 over 2 to the power m minus 1 equals to 1 over 3 to the power of m. Now, is such an equation possible? Actually, despite the hard-looking equation trick here, it's like quite readily can be solved, because we just need to rewrite it like that. Take a difference of 2 fraction equals to 1. Always suitably just multiply by 1 factor. Let's say I want to make this side bigger. So I just multiply by 3 to the power of m. Aha! Then this becomes 3 to the power of m times this is 1. This is 3 to the power of m. So rewriting this, we can see the contradiction quite readily. If it's not obvious, please take note that on the next line, aha, 3 to the power of m, 2 to the power of m is equals to 3 to the power of m plus 1. It's all positive integers, the m part. Now, please take note. Oh, sorry. Did I write m instead of n? Okay, just rewriting that. Just change the m to n. I think wrong in the argument. This is depend on the index sensitively. Okay, so this is m, this is n actually. So to multiply by 3 to the power n, so it becomes something like this. So this is an integer. So if this is an integer, because on the right hand side to the power n plus 1 is an integer, this must be an integer. That means 2 to the power of m divides 3 to the power of n, a contradiction. Because these primes 2 and 3 have no common factor. That's one common trick for exponent Diophantine equations like this. Because GCD of 2 and 3 is 1, no common factor. How can it divide? Primes are unique by itself. Okay. That's the case where mx is less than 0. So we go for the next case 2, please. When x is bigger. Sorry, we put like this. Okay, x is bigger equal to 0. Up to, let's say we can just suitably take. Let's be like take no problem. Let's say we just suitably take up to 4. Actually, 3 is enough. Okay. And 3 is sufficient. Actually, I put 3, make it more professional. So in this case, I'll tell you why on the third case, you'll understand. So we just, that means x is 0, 1, 2, or 3. So we just try each case manually. Please substitute like that. 2 to the power of 0, that means that easier way would be to put the 3 to the power of y on the left and put it equals to 2 to the power of 0 minus 1. Then just check, solve manually, please. Like that, 2 to the power of 1 minus 1, 3 to the power of y, 2 to the power of 2 minus 1 equals 2, and 3 to the power of y, 2 to the power of 3 minus 1. Aha, 0, 1, 2, 3. So when you subtract that, 1 minus 1 is 0. Aha, this one is 2 minus 1 is 1. So 4 minus 1 is 3, 8 minus 1 is 7. So the integer solutions are only for these two, because only these two can be written as like 3 to the power of 0 in the index form, 3 to the power of 1. These two cannot. So that means this yields the appropriate y as 0, and here y is 1, from which we deduce the solutions for this question, the integer solutions, which are xy equals to, the second one, the x is 1 again, x is 1, y is 0, or x is 2, and the y is 1. So it's only two solutions here. So we have one last case here. And what is that case? And how do we solve reaching to that? So just a challenge for the third part. Okay, let's take a closer look how to solve this part. Yeah. Okay, no worries. Let's just continue. So the third case is, as you can see, y is separated now. It makes sense because I experimented with it a little bit earlier just now. Okay, so the case 3, so this is how we do these kind of equations. Just guidelines exist, but there are no like you must do this or must do that or that. So did I do the case 3, 8 minus 1, right? So x is at least 4 now. Aha. So the last case, what happens if x is at least 4? Okay, the first thing I would like to notice, I said 4. Okay, now minus, since we already put it like that, it's not the optimal. I think 3 will be better. Playing with modulo 4. Modulo 4 means 2 to the power of x is divisible when x is equal to 4 by 4, because 2 times 2 times 2 is going to be 16 actually, in fact. So we have over information. So we say that 2 to the power of x is congruent to 0 mod 4. Aha. And please remember that in modulo terms or in remainder, 3 is congruent to negative 1 mod 4. That means 3 when divided by 4 is same as having a remainder of negative 1. You think of it like that. Okay. So substituting these 2 into the modulo, that means the given equation. So equations must be true not just in equality, that is in value, but also in terms of remainder, for example. So that is why the congruence discovery was phenomenal. So this is 0 minus 1 like that. We change this to 3 lines. Modulo 4 can also do a subscript like that. And the 3 we just replace with negative 1. All these are modulo laws. To know that, you need to consult some nearby books, or maybe time permits in the future, you can do videos on that. Okay. But let's try to take it like you know this already. So negative 1 to the power of y is congruent to y, negative 1 mod 4. So this is same as is only if, like just like normal equation, the power y must be odd, because only odd power get negative 1, right? Yep, that part we can just deduce like that. So sometimes we learn how to use it first before understanding its details of the congruence. So let y equals to, since y is odd, let's say I just suitably choose y is to k plus 1. Okay, the case k is 0, and then k I just put as a non-negative integer, because to include the y from 1 onward. Okay, what would happen to the original equation? Always substitute back in the original equation. So in this case, this would be 2 to the power x minus 1 equals to 3 to the power of 2k plus 1. Okay, let's rewrite the entire thing, please. So we rewrite the entire thing like this. Let's move it here. Please take note. Equals to 3 times 3 to the power of 2k, because 2k plus 1 can split it, plus 1. Aha. Okay, now let's think about this. What is the problem? What is the contradiction that can arise from here? Or are there solutions from there? See, we want to maximize. See, remember that now we look at modulo 8, bring it up to the next level, because x is sufficiently big enough. So 2 to the power of x is going to have at least, what do we say, 3, right? 2 to the power of 3 inside it. So it's going to be 8 times something at least. So that is why we modified this side first. So I wasted a while to rewrite like this. So 3 squared is 9 to the power of k. Aha. Because 8 coincidentally, the numbers they choose to have some kind of weird coincidences sometimes, is that, so we use the two facts that now I noticed that, but 2 to the power of x is congruent to 0 mod 8. So sometimes I write like this, or sometimes we can write like this. 9 is congruent to, when divided by 8, remainder of 1. That's what it means, 9 divided by 8, remainder of 1. So 9 to the power of k, what you do is just as simple as just adding a power k, like normal equation. Oh, so modulo y is just congruent to 1. So looking at this equation modulo 8, let's look at it modulo 8. Just using some big words so you'll get used to it. That doesn't seem a big term anymore. I'm not so good in all this. Just a little bit here and there. To share what we know. So look at it modulo 8 plus. So what happens is when you replace it in 3 lines, so it becomes 0, it's congruent to the 3 just maintains itself. 9 to the power of k can be replaced in modulo 8 as 1. And then there's a plus 1 just now, just copy that. You can see the thing. So from here, the 9 to the power of k, we replaced it as 1. The rest is just copied from the equation. Please take note how the equation we only replace modulo 8. So the 2 to the power x becomes 0. So in other words, this tells me that something like this in reverse, 3 times 1 plus 1 is 4. That means basically what it's telling is 4 is congruent to 0 mod 8. See, 4 congruent to 0 mod 8 is a contradiction, because there's no such thing, because it's telling me that 4 leaves a remainder of 0 when divided by 8 or multiple of 8. 4 is a multiple of 8, all as equivalent statements. So, which is impossible. Okay. So this contradiction tells me there are no other solutions. So the earlier two solutions are the only ones. Thank you.